first transistor M1. So what we are doing here is we are giving the input to the first transistor M1. So Vin is the input to the first transistor. Biasing is of course there. V bias is the biasing. So you bias the transistor for amplification. By biasing, what you do is you fix the Q point such that the excursion is within the load line. And the transistor operates in its linear region. So if it goes beyond the linear region, it will not operate as an amplifier. So it operates within the linear region. That is what we ensure. So biasing is done in a manner that the Q point is at the center of the load line. So excursion will be limited to the load line. So that is how you bias the transistor, whether it is BJT or it is KPT. The purpose is to fix the Q point at the center of the load line. Once you determine which load line you are going to use, at the center of the load line you fix the Q point. Of course, if you go to power amplifier, then it will be different. Class B amplifier, Class A amplifier, or Class C amplifier. There you will fix it at one of the ends of the load line, and we will use two amplifiers, one to push, other to pull. So for pushing one amplifier, pulling one amplifier in case of a biased amplifier. Here we are considering not a Class B amplifier, not a power amplifier, normal amplifier, but we want to increase its gain. Therefore, two amplifiers are in cascade. So M1 is one amplifier, so the FET for the first amplifier where you are giving the input, then the output of M1 goes to the second amplifier M2. So first it will be amplified by M1, then the amplified version will again get amplified by M2. So there will be net amplification will be high in this case. So in this case, only thing is the M2 is acting as a load to the M1, because output of M1 goes to M2. So M2 acts as a load to the M1. Now when M2 acts as a load to the M1, for proper coupling we use a capacitor there. So we have a C fixed, that you can see at the V output there is a C fixed. So there is a, for coupling we are using a capacitor, C fixed. So to isolate that capacitor, the load capacitance, if we want to isolate it from the first transistor M1, then we use, as you know, capacitance, its opposite is inductance. Therefore we use series inductors. So they will isolate the load capacitance from M1. Now when you have LC in series, that will, because of L, the charging of the capacitance will be delayed, because L itself will have a time constant, R by L. For capacitance, time constant is 1 by RC. When you have inductance, time constant is e to the power R by L. So that way there will be a delay. Because of that there will be a delay. So that delay will delay the charging of the load capacitance. So what is the effect of that if it is delayed and charging of the load capacitance is delayed? The effect is it will delay the bandwidth and the delay. The delay will trade for the bandwidth. So the more the delay, the less is the bandwidth. The less the delay, the more is the bandwidth. So it trades with the bandwidth. So if you want to increase bandwidth, then you decrease the delay. So accordingly we fix the values of L. So if you have smaller L, low delay, then bandwidth is more, but you know bandwidth into gain is constant. Gain bandwidth product is constant for amplifier. So bandwidth will be low, bandwidth will be more with smaller delay, but gain will be less. So if you want to have a peak gain, then bandwidth can be smaller, gain can be larger. For bandwidth to be smaller, we use larger delay. For larger delay, you use or choose accordingly L2 and L3. Now L1, L2, L3, all these three inductors, they can be implemented by two coupled inductors with coupling coefficient K, that you can also see here. L1, L2, L3, they can be replaced by two coupled inductors. So take two inductors, couple the inductors like mutual coupling. So instead of three inductors, we can have two coupled inductors with coupling coefficient K. So either you use these three inductors or you use two inductors, they are mutually coupled to each other. So only L2, L3, there will be no L1, but L2, L3 will be coupled. They will not be in series, they will be coupled with a coupling coefficient K. That also will do the same thing. So this is just shown here. In this case, look at the left figure is the figure that we saw in the previous slide. It's equivalent when we use coupled inductors. You can see L1 and L2, they are coupled inductors. So we have coupled inductors there. So this one is replaced by a coupled inductor. Otherwise it is same. Now when you have coupled inductor, there will be inherently a capacitance. So that is CB. Coupling coefficient is K. Otherwise the circuits are same circuit. L1, L2, L3, they are replaced by coupled inductors, L1, L2. All other parts are same. You can see all other parts are same. So the coupled inductor, this uses coupled inductors to realize a T-inductor network. Here you can see that we have used a T-inductor network using coupled inductors. This will be performing best if the capacitance at the drain of M1 is much less than the capacitance being driven by the output flow, which means CB is much less than C fixed. So driven capacitance at the output load is C fixed. CB is the capacitance at drain, so that will be small. And the CB provides parallel resonance because LC, now you can see this L and C, L1, L2 and CB, they are forming a tank circuit, which is a resonator circuit. So it is a parallel resonance circuit. This parallel resonance improves the bandwidth further. Why it will improve the bandwidth further? Because once you have a resonator, it will resonate at a certain frequency. But when it resonates at a certain frequency, it will have a bandwidth, its own bandwidth. So the whole circuit will work over that bandwidth as well as the bandwidth of the amplifier itself. So two bandwidths are there. One is the bandwidth due to the resonator, CB and L1, L2, that bandwidth, and the bandwidth of the amplifier. There will be an overlapping between these two bandwidths. Due to overlapping, you will get a net bandwidth, which is more than the bandwidth of the amplifier as well the bandwidth of the parallel resonator, LC resonator. So therefore, CB will provide a parallel resonance, and that resonance will improve the bandwidth further. Details you can see from the book that we have tested. It's on this book that you can see. Now, let us look at what happens analytically. The self-inductance L with the other winding open circuited must be L is equal to RL square CL by 2 into 1 cross K. This is a requirement how to choose the inductances. There you saw L1 and L2, those L's should be this. L is equal to RL square CL by 2 into 1 plus K. RL square is the load resistance, CL is the load capacitance, K is the coupling coefficient. So using this, you have to find out what is L. Now on the self-inductance L with the other winding open circuited must be this is the capacitance. CB must be equal to CL into 1 minus K by 4 into 1 plus K. CL is the load capacitance that you know. So from that we have to find out what is CB. So CB has to be equal to CL into 1 minus K by 4 into 1 plus K. Now what will be the coefficient, coupling coefficient for the inductors? The coupling coefficient for the inductors will be equal to 1 by 3 if you go for a Butterworth type of response, and K will be equal to 1 by 2 if you go for a maximally flat delay or a linear phase. Now you may ask me what is Butterworth response, what is maximally flat delay or maximally flat response. That means actually maximally flat means it is like it remains flat over the bandwidth, over the operating bandwidth. It will remain flat. The response will remain flat. Response will not change. It will not increase or decrease. It will remain almost flat. So most of the time within the operating bandwidth, if it remains flat, which means it is a straight line or it is parallel to the frequency axis, then it is called maximally flat. But if it is like the Butterworth response, so it is like butterfly, wings of a butterfly. So you look at this response. The response is not flat completely. It is mostly like wings of a butterfly. Then you call it a Butterworth response. So K is equal to 1 by 3 for a Butterworth type of response. K is equal to 1 by 2 for maximally flat response. To extend the bandwidth, so bandwidth extension requires K is equal to 2.8. So approximately a Butterworth response. So the maximally flat will be always over a small region. Flat response is over a small region. Therefore, we always look for a Butterworth type of response to increase the bandwidth. So if you have a larger bandwidth, if you want a larger bandwidth, then we have to choose K is equal to 2.8, which is approximately a Butterworth response. Suppose we are using a MOS transistor and we want to find out what will be Ft. Omega T is equal to Gm by CGS plus CGD. Gm is transconductance, you know. CGS capacitance between the gate and source, CGD gate and drain. So that is also equivalent to or approximately equal to Gm by CGS, because in case of MOS, CGD or capacitance between gate and drain is very small compared to capacitance between gate and source. So that gate and drain capacitance can be neglected. So omega T is approximately equal to Gm by CGS, from which you can find out what is Ft, because omega T is equal to 2 pi Ft. Ft doubler, that in the amplifiers, it attempts to increase the ratio of transconductance to capacitance. So if you want to increase, if you increase the Ft, which means the ratio Gm by CGS will increase, because 2 pi Ft is equal to Gm by CGS. 2 and pi are constant. Now if you increase Ft, Ft can be increased only if Gm by CGS is increased. Therefore, Ft doubler in amplifiers, they attempt to increase the ratio of the transconductance to capacitance. Now, we make these arguments that a differential amplifier, look at the figure. The figure gives you a differential amplifier. Two amplifiers, M1 and M2 are there, which is a differential amplifier. In the difference mode, they are connected in difference mode. They are not in series. You can just see the output of the amplifier 1 is not going to the input of amplifier 2. They are in differential form, like the what you call the operational amplifier. If you look at the operational amplifier circuit, operational amplifier is also a differential amplifier. So this is a differential amplifier. We have discussed about differential amplifier earlier. The difference between the outputs of the amplifiers is amplified. So we make the argument that difference amplifiers are Ft doubler, because capacitance seen by V in for single-ended input is CGS by 2, because we have two amplifiers in difference mode. So the capacitance now becomes CGS by 2. Difference in current I2 minus I1, that is equal to V in by 2 Gm minus V in by 2 into Gm. I2 is equal to V in by 2 Gm. I1 is equal to, because it is in difference mode, so I1 is equal to minus V in by 2 into Gm. So I2 minus I1, difference in the current, is equal to V in into Gm. Transconductance to capacitance ratio, that is doubled, because Gm by CGS, in this case CGS capacitance now has become CGS by 2, therefore Gm by CGS by 2, that is 2 Gm by CGS. So because of that, the transconductance to capacitance ratio is doubled. Since transconductance to capacitance ratio is doubled, this is a Ft doubler. Now, let us look at how to create a single-ended output. The input voltage is dropped across the two transistors. Reason is because they are in difference mode, so the input voltage is again dropped across the two transistors. That results in the ratio given by voltage divider in the capacitance, which is ideally 1 by 2 of the input voltage on CGS of each of the devices. Now, an input voltage source, and that source is the series combination of the capacitances of each of the devices, M1 and M2. So, for V in will see a series combination of the capacitances of each device. Ideally, it will see 1 by 2 of CGS. Why? Because CGS, when you consider the ideal case, M1 and M2 both are ideally equal transistors, same transistors. So they will have same CGS. And their CGS are connected in parallel series. When they are connected in series, two capacitors C in series with C gives you 1 by 2C. Net capacitance is 1 by 2C. So therefore, ideally it will see 1 by 2 of the CGS of M1. Currents on each device will add to ideally yield a ratio 2 CGM by CGS. Now, based on this analysis, you can say that this difference amplifier we can also have as equivalent to the amplifier shown on the right hand side. We have V in as the input to M1. For M1 there is V bias. For M2 there is I bias, which is coming from the M1. So we have an I bias. I bias will be same for M1 and M2. Then I0 is coming to M1, and M1 is connected to M2 not in difference mode. You can see now it is not connected in difference mode. But it is almost like a cascade amplifier, although it is not exactly cascade, but it is something like a cascaded combination. Now, use the current mirror for biasing. Here what we have done is look at the first amplifier. Left side is the first amplifier, which is the difference amplifier. In the difference amplifier, the current that we see is 2 I bias. 2 times I bias is the current. Corresponding to V bias, the current is 2 times I bias. That we divide in the second amplifier. Its equivalent, as we discussed in the previous case. In its equivalent case, the current is divided between the two devices M1 and M2. In each it will be I bias. Okay. Then we look at the equivalent using a cascade, proper cascade connection, which is the third one, the last one. In the last one, to realize I bias for the M1, we use another device M3. So M3, if you look at M3 is connected in cascade to M1, and that gives us, if M1 and M2 both have the same device, they have same characteristics, exactly same characteristics, then we'll get I bias given to M1 because of M3. Then you have M2 as it is, so the ultimate equivalent circuit is this, the right hand side. So instead of using a difference amplifier, you can use an amplifier which is shown in the right hand side, but it requires one more device. So what we do is we are using current mirror for biasing, mirroring the current. This is from bipolar circuits or BJT circuits. In this, you need to set the V bias such that the current through M1 has the desired current of I bias. So that we have ensured. When that is done, then the current through M2 will ideally match that of current M1. So, and that is what is happening in this case. Now, if we use the FT doubler, what are the problems that we face? Particularly in modern CMOS RF circuits, the problems that we face are, first problem is it works if CGS dominates the capacitance. But in modern CMOS circuits, this is not possible. CGS will not dominate the capacitance. For example, CGD will be 0.45 times the CGS in 0.18 CMOS. So CGS is not dominating the capacitance. CGD is almost half of CGS. So CGS is not dominating. CGD cannot be neglected. So that is a problem if you use modern CMOS circuits. Then second problem is the available bias voltage across M1 or M2 is severely reduced. This is reduced by a factor of 2. So the bias voltage is reduced by a factor of 2, and thereby it reduces the effective FT of the device. So it will no more be FT doubler because the bias voltage reduces in CMOS devices. Then the third problem is input capacitance that will degrade due to CGS, CDB, or of M3 due to the CGS and CDB of the M3. So at most 1.5 times improvement in transconductance capacitance ratio can be achieved. So you cannot achieve more than 1.5 times improvement in transconductance capacitance ratio, which means you cannot have a FT doubler, because transconductance capacitance ratio should be doubled to get a FT doubler. So you cannot double it, you can go up to 1.5 times. So input capacitance degrades due to CGS, CDB of M3, that restricts the doubling of transconductance to capacitance ratio. So even if we assume that CDB is 0, then also Cin is equal to, or input capacitance is equal to CGS in parallel with 2 CGS, which is equal to 1 by 1.5 times CGS. It is not 1 by 2 times CGS, so you will not have 2 times the FT. So these are some of the problems. Then let us look at how we are going to increase the gain bandwidth product using cascading. So we are seeing 3 amplifiers connected in cascade. So amplifier 1 connected to amplifier through cascading. Between them there is a C fixed. Similarly, amplifier 2 to amplifier 3, there in between them there is a C fixed. And now if you do the analysis, this Laplace analysis or Fourier analysis, then if you give V in as input, then the transfer function of the amplifier, first amplifier, the transfer function of the first amplifier is A divided by 1 plus S by omega 0. So V in, that will go to the transfer function of the first amplifier. Each amplifier will have the same transfer function A by 1 plus S by omega 0. So the V out by V in will be how much? V in, V out by V in will be transfer function raised to the power n if there are n number of amplifiers. If amplifier is only one amplifier, Then V out by V in is the transfer function A by 1 plus S by omega 0. If there are n transistors, then it will be V out by V in is equal to A by 1 plus S by omega 0. That we can write as A to the power n into 1 by 1 plus S by omega 0 to the power n. Now the question is, how many amplifiers we can use? Can we increase it infinitely? That is the question. Now that you have to answer. Look at the book and answer. Let us do the derivation of the overall bandwidth. Overall 3 dB bandwidth of the amplifier is where V out by V in is equal to A divided by 1 plus J omega 1 by omega 0. This is V. Omega 1 is the edge of the frequency. Omega 0 is the center frequency. Omega 1 is the edge of the frequency. So edge of the frequency means if you do edge of the bandwidth. Sorry, not frequency, edge of the bandwidth. So if the bandwidth is there, there is a bandwidth means there is a range of frequency. So suppose it starts from F1, goes up to F2. Lower frequency is F1, upper frequency is F2, center frequency is F0. So F0 is usually F1 plus F2 by 2. So in that case, what will be F1, what is F2? If you know what is F1, F2, what is F2, how do you find out what is F1, what is F2? If you consider 3 dB bandwidth, then at the F1, the gain is V out by V in. Gain should be maximum gain divided by root 2. What is the maximum gain? Maximum gain is A to the power n. That is the maximum gain or gain at the center frequency. So that will be the maximum gain. So it is An by root 2. V out by V in is equal to An by root 2. Omega 1 is the overall bandwidth. A and omega 0 are the gain and bandwidth of each section. So A divided by root over of 1 plus omega 1 by omega 0 square whole to the power n is equal to An by root 2, because A and omega 0 are gain and bandwidth at each section. Now if you equate these both the sides, then we will get 1 plus omega 1 by omega 0 whole square to the power n is equal to 2, or omega 1 is equal to omega 0 root over of 2 to the power 1 by n minus 1, which indicates that bandwidth decreases much slower than the gain increases. So if the gain is increasing, with that bandwidth is not decreasing in proportion. It decrease in bandwidth is much slower if you use a cascading. Overall gain bandwidth product of the amplifier can be increased. From this we get this much of information. This shows you the transfer function of a cascaded section, normalized transfer function for the cascaded section. On the x-axis is the normalized frequency, on the y-axis is the normalized gain. You can see that when n is equal to 1, which means number of transistor is equal to 1, and when number of transistor is equal to 4 or 5 or 6, that way the bandwidth is not changing much. Again, although gain is increasing, the bandwidth is not changing much. So we can increase the gain without affecting the bandwidth to a large extent using cascading. Okay. Now how many stages we are going to use? Choosing the optimal number of stages. to first order approximations, there is a constant gain bandwidth product for each stage. In each stage, gain bandwidth product is constant, not the overall. So if you have n stages, over the n stages, gain bandwidth product is not constant. Over each stage, it is constant, which means A into omega 0 is equal to omega u being the upper bandwidth. So A into omega 0 is equal to omega u, or omega 0 is equal to omega u by A, which means increasing the bandwidth of each stage requires that we can make up for the lost gain by cascading more stages. So if you want to increase the bandwidth of each stage, so once you increase the bandwidth, gain will be lost. That we have to make up. So to make up that, how do you increase the gain? By cascading more stages. That is what we do. Now we have found out that overall bandwidth is calculated at calculated as lower its gain. So omega 1 is equal to omega 0 root over of 2 to the power 1 by n minus 1. This we have found out. Now omega 0 is equal to omega u by A. So that we can put. So omega 1 is equal to omega u by A root over of 2 to the power 1 by n minus 1. Assume that we want to achieve gain G with n number of stages. So we are going to use n stages and gain is G, which means A is equal to G to the power 1 by n. Each stage will give you gain G. Each stage will give you gain of G to the power 1 by n. Then if you use n number of stages, so G to the power 1 by n whole to the power n is equal to G. So that way A is equal to G to the power 1 by n. If you want to use n number of stages to reach a gain of G. So A is equal to G to the power 1 by n. Now you can find out what will be omega 1. Omega 1 is equal to omega u by G to the power 1 by n root over of 2 to the power 1 by n minus 1. So from this equation, we can always find out the optimum gain per stage, which is equal to square root of E, which is 1.65. So optimum gain per stage is equal to 1.65. For details derivations, you can see the book. Look at the book of Tomlin. This figure shows you what we discussed. The whole thing is shown here. The achievable bandwidth normalized to omega u versus gain and the number of stages. So for different A, you can see A is equal to 3, A is equal to 1.65. When we have A is equal to 1.65, we have the ratio of omega 1 to omega u much larger compared to when we have A is equal to 3. Gain is equal to 3 of the amplifier, single amplifier. Similarly, gain becomes G is equal to 1000, G is equal to 10, G is equal to 100. All those are shown here. What will be the number? How many amplifiers you require? So for G is equal to 10, you require for peak, you require 5 amplifiers. For G is equal to 100, you require around 7 amplifiers. For G is equal to 1000, you require more than 10 amplifiers, around 10 to 15 amplifiers. That will give you G is equal to 1000. So we can dramatically lower the power and improve the noise by using larger gain per stage. So this motivates us to use distributed amplifiers or cascaded amplifiers, whatever you say. So distributed amplifiers, motivation for distributed amplifier is this. We achieve higher gain for a given load resistance by increasing the device size. By increasing the device size, we increase the transconductance. This with this increased capacitance, they lower the bandwidth. We therefore get a relatively constant gain bandwidth. We know that transmission lines that we are using in the circuit, they have ideally infinite bandwidth. This is ideal, but actually their bandwidth is limited. But they can be modeled as LC networks. Since transmission lines can be modeled as LC networks, we can use them as equivalent lump device capacitances into transmission lines. So we can lump device, we can use device capacitances into the transmission line in the analysis. So now, if we do that, let us see what is the effect in distributing the input capacitance along the transmission line. So the lump input capacitance into LC network corresponding to a transmission line will result in signal ideally CZ0 is equal to RL rather than an RC low pass circuit. The signal that you are giving input, that will see the load as RL, Z0 is equal to RL if it is terminated in the characteristics impedance. Often we implement it as a lumped network such as T-coils, etc. We can now trade the delay rather than bandwidth for the gain. So instead of compromising with gain, we can compromise with delay. So you trade with delay, you can give more delay. Each transmission line is equivalent to a delay circuit. Why it is equivalent to a delay circuit? Because it is equivalent to an LC circuit. From transmission line equivalent circuit, we know transmission line is equivalent to an LC circuit, L in series, C in shunt. So that is what it is. Therefore, it is an LC circuit. LC circuit introduces delay. So each section of transmission line is introducing delay. We can trade this delay rather than the bandwidth for the gain. Issue is outputs are delayed from each other. At each section there will be a delayed output. That is the issue. That there are methods of taking care of that. The delayed output can be taken care of. So delay the outputs by same amount as the inputs. So that way we will take care of the output delay. That you can see here now. In the bottom part there is a series of transmission lines. So Z0 you can see 1, 2, 3, 4 Z0s. In the bottom each is a transmission line section. Similarly, in the top part we are equivalently we are using 4 delays. So they will take care of the delays at the input. The delays in the output will take care of those. So delay the outputs by the same amount as the inputs. Now those signals will match up. We have also distributed the output capacitance. Benefit is high bandwidth. Problem is high power, poor or noise performance because of the transmission line. Expensive in terms of chip area. It requires more chip area because you are adding transmission lines. So transmission line will require physical area. So it will require more area in the chip when you design the chip. So expensive in terms of chip area. So this is the negative. Each transistor gain is adding rather than multiplying. That is another problem here. Then we will come to the narrowband amplifier. Particularly this up to now we have discussed broadband amplifiers. Now let us start discussing the narrowband amplifiers. For wireless systems, mostly we are interested in conditioning and amplifying the signal over a narrow frequency range centered at a high frequency. This allows us to apply narrowband transformers to create matching networks. So mostly we are dealing with narrowband amplifiers, not broadband amplifiers in the wireless system. How can we do this? We can take advantage of this fact when we are designing the amplifier. Can we take the advantage? Look at the figure, what we have. We have a connector, then we have a controlled impedance PCB trace. What is controlled impedance PCB trace? We have that is basically a microstrip line, and depending on the width of the microstrip line, the impedance will be, characteristics impedance will be determined. So that is under our control. The width of the microstrip line is under our control. So we control the impedance of the connecting line of the PCB trace. So there is a connector. From the connector is connected to a matching network through a controlled impedance PCB trace. Then the output of the matching network is connected to the packaged chip. So in the packaged chip is connected to the output of the matching network. Its equivalent circuit you can see. The connector is connected to a driving source. So V in is connected to the connector. So driving source will have Z1 as its driving impedance. Then because of the PCB trace or the controlled impedance line, we have a delay which is X. Our characteristics impedance is the Z0 of the transmission line. Then you have the matching network. Then on the chip, in the chip what you will have? You will have LC circuits, RL, and then voltage, load, and that will be connected to an amplifier. So from the amplifier you will get the output. So this is basically the amplifier design. The amplifier and its design is basically this. Now the amplifier we have to, since we are using a narrowband amplifier, the amplifier is to be tuned to a desired frequency. So to tune the amplifier to a desired frequency, put an inductor in parallel across the load resistor. So that will create a band pass filter with a center frequency that the amplifier will be tuned to that center frequency. So it will turn out that the gain bandwidth product is roughly conserved because of this, because it is using a band pass filter. So it is roughly conserved regardless of the center frequency. To see this issue and other design issues, you need to look further at the parallel resonance circuit. Otherwise, if you don't remember, try to read out once more the parallel two types of resonance circuits: series resonance circuit and parallel resonance circuit. If you remember the parallel resonance circuit, it will be easy to design it. Now, for tuned amplifier, the transfer function around the resonance is V out by V in, that is the transfer function, that is GM into Z tank. Z tank is the impedance, V out by V in is GM. Z tank is equal to GM by Y tank. V out by V in is equal to GM into Z tank. Z tank is the impedance of the tank circuit. So GM into Z tank, that is equal to GM by Y tank, because Z is equal to 1 by Y. So V out by V in is equal to GM by Y tank. Now conductance is in parallel. When conductance is in parallel, look at the circuit, on parallel circuit, parallel resonance circuit that is given below. For the parallel resonance circuit, Y tank is equal to 1 by RP cross 1 by S into LP, that is the admittance of the L, cross S into CP. This you know from the Laplace analysis of a parallel resonance circuit. This you know. Now at S is equal to j omega. Y tank omega will be equal to 1 by Rp plus 1 by S into Lp. 1 by S into Lp is 1 by j omega into Lp, which is minus j by omega Lp plus j omega into Cp. So that you can write as 1 by Rp plus j by omega Lp. You take that common. So that will give you minus 1 plus omega square Lp into Cp. Now, if you look at the narrow band around the resonance is at omega 0. Narrow band around the resonance is delta omega. So we will consider the frequency range omega, which is equal to omega 0 plus delta omega. Then Y tank over delta omega is equal to 1 by Rp plus j by omega 0 plus delta omega. That is for omega. We are writing omega 0 plus delta omega. So that into Lp whole into minus 1 plus omega 0 plus delta omega square into Lp Cp. That is approximately equal to 1 by Rp plus j by omega 0 Lp into minus 1 plus omega 0 square Lp Cp plus 2 omega 0 delta omega Lp Cp. Now we have seen what is Y tank in the previous slide. That is approximately equal to 1 by Rp plus j by omega 0 Lp into 2 omega 0 delta omega Lp Cp, because omega 0 square Lp Cp will be approximately equal to 1. So they will cancel out. So that is equal to 1 by Rp plus j delta omega 2 times Cp. So the simplified RC circuit for the bandwidth calculation is this. For this, the Z tank will be approximately equal to Rp in parallel with 1 by j delta omega 2 Cp. And its characteristics you can see. Omega 0 is the center frequency. On each side we have a frequency of 1 by Rp 2 Cp on both sides. So total bandwidth will be 1 by Rp into Cp. Slope is minus 20 dB per second. When from the peak, when it is coming to 0, as the gain reduces to 0, the slope is minus 20 dB per decade, which means it decreases by 20 dB for every 10 frequencies. Which means at the edge, suppose it is F1, then at F1 it is 0 dB, then at 10 F1 it will be minus 20 dB. That is what is meant by minus 20 dB per decade. Now you can see the comparison between the low pass and band pass figures. So low pass, you can see low pass is the top one, band pass is the bottom one, and in the band pass the bandwidth is narrower than the low pass. So using a band pass thing, we are getting a narrowband amplifier. It is easier to get a narrowband amplifier if you use band pass or tuned amplifier instead of a low pass amplifier. Here is a comparison between low pass and band pass. Tuned amplifier characteristics is a frequency translated version of the low pass amplifier, or the band pass characteristics is a translated version of the low pass amplifier. Band pass bandwidth is equal to the low pass bandwidth. That is, the bandwidth set is 2 times narrower than the upper and lower sidebands, giving the same bandwidth as low pass. We are tuning out the effect of capacitors in this case. Parallel LC looks like an open circuit at resonance. so C does not load the amplifier. This is often called the low pass to band pass transform of filter design. If you will read filter in your communication circuits, you will understand this. Replace C with parallel LC circuit. Replace L with series LC tank circuit. So for the gain bandwidth product of the tuned amplifier or the narrowband amplifier is G into bandwidth, gain into bandwidth is equal to GM into Z that we have seen. So Z is equal to Rp into 1 by Rp Cp. So that is equal to Gm by Cp as in the previous. So this expression is just like the low pass and is independent of a center frequency. In practice, you need to operate at a frequency which is much less than Ft of the device. With that, we come to the end of today's class. We'll see in the next class. Attendance nahi hai chuka. So we have taken the attendance. Don't worry about the attendance. Thank you.